Good afternoon, everyone. My name is Timothy Aluko. I'll be presenting to you this afternoon on climate winds data, which predicting climate change with machine learning. The introduction. The issue of climate change has been a vocal issue over the years, leading transformations through science with the integration of machine learning. This approach has been successful through data-driven methodology to tackle the complexity and scale of global climate system, providing actionable insight for mitigation and adaptations. And as a result, a rise in severe weather events has put many communities in jeopardy. So climate winds solutions are able to leverage on this to enhance safety and analyze the weather pattern in the European countries over the years. The main objective of this presentation is to focus on the using of machine learning by climate winds to one, safeguard human safety and well-being. Two, to determine whether abnormal weather patterns are becoming more common in Europe. Three, is to identify the weather pattern that deviates from regional norms. And four, is to use the current trend, forecast potential future weather conditions over the next 20 to 50 years. And the last objective is to determine which European country or cities will be the safest for people to live in over the next 25 to 50 years. So the data requirement for this historical weather analysis are one, the satellite and radar imagery. This is to contextualize the virtual of weather changing pattern for deep learning modes. And two is a real-time weather situations to understand the immediate model updates to improve weather forecasts and for accuracy purposes. The third one is topographical and climate zone data. This to understand the impact of geographical locations or regional weathers. And three thought experiments are performed. One is predicting weather anomalies, which is to assemble model that analyze weather patterns, focusing on using analysis shift in weather pattern based on historical data. The second one is deep learning, that's convolutions neural network, CNN, which process satellite imagery to detect climate change indicators like deforestation and glacier melting. The last one is GAN for weather projections. This is also generate possible future weather scenarios using GAN to stimulate weather variations. So our first results was based on the random forest model for all the stations in Europe. You can see from this table, this graph, that the Bliss is the most important stations, followed by Kassel and Budapest. This is decade data from from the year 2000 to 2009. So by analyzing vast data such as satellite image, historical record, and real estate climate data, the machine learning model uncover patterns and interaction invisible to traditional approach. So this revealed the weather pattern parallel to deviations, providing insight into local weather trends and improving climate winds data analysis. The chart shows that the Bliss, Kassel, Budapest, Oslo, and Stockholm are the most important features in the outcome. The model accuracy improved by 67% after the optimization. The decision tree from both models are complex to interpret, although while the unoptimized tree is deeper with more layers and split, the optimal version is simpler. So there are some notable differences in the bar chart after the optimization, we can see that the bleed still is still the most important, still remain the most important station in both charts, and also increase in importance more than optimization. The Kase, which was in the previous chart, was number 2, dropped from second place to fourth place after optimization, while Budapest, which is the third place in the first chart, moved to second place in the optimized chart. Munishev ranked last in the ranking in the first data, but rose to the second most important position after the optimization, demonstrating its increase in importance. The optimized chart therefore reflects a rebalancing of weather station importance, giving more weight to dominant stations like the Bliss, Munas, and Kassel. Thereafter, a diagram and a clustering analysis was performed. We can see the complete method and word model were now presented. On the complete model, that is a nice mix of cluster, locations, or time of year could cause this. Then on the word model, on the word method, this show 2 cluster. So the complete model offer a more details, virtual representations of data pattern by comparing the maximum distance between the cluster. This approach cluster the data, if you can see in this diagram, including both on scale and reduced form. These are evenly distributed based on the cluster. You can see these diagrams are evenly distributed, offering a balanced view of relationship within the dataset. Based on this information, it is ideal to apply unsupervised algorithm for future analysis. Then on JAN, the JAN stimulates future weather scenario, revealing potential pattern. You can see the model reached 97.7 accuracy after 50 epochs. And the validations accuracy is 88.39%. And the loss is 0.98%. A 10% accuracy gap between the training and validation set, primarily due to misclassified cloudy conditions, as Sonny suggests, insufficient. So this model requires 30 epochs to reach an accuracy of 95%, and require another 20 epochs to reach an accuracy of 97.7%, as we can see. So a combination of 20 and 30s make it to reach 97.7 accuracy after epoch. The confusion matrix shows that the poor performance is mostly due to false prediction of weather in class O, classifying cloudies as shine. This might be due to lack of sufficient data in training data set for this analysis. The key machine learning contributions in this case is the machine learning one is extreme weather events, which we've noticed from the prior presentation. The machine model predicts hurricane, flood, and drought, providing critical lead times for disaster preparedness and reducing risk to human life and properties. Also, the carbon footprint tracking. The algorithms are used to monitor and quantify greenhouse gas emissions globally, helping policymakers target reductions strategically effectively. The last one is land and ocean dynamics. The machine learning analyzes the ecosystem, that is the vegetation change, ice sheet dynamics, and ocean temperature to improve ecosystem and biodiversity's conservation efforts. Challenge for machine learning for climate change. One, the most of the greatest challenge and limitations is data. Unequal global data availability and inconsistency across sources can hinder model accuracy and generality. 2 is model transparency. The complexity of machine learning model can obscure their decision-making process, raising trust and interpretability issues. The last one is resources intensities. High computational and energy demand of large-scale machine learning model can limit their accessibility and sustainability. What does this give us in terms of opportunities for future potentials? One is hybrid system. Combine physics science-based model with machine learning for more accuracy, climate change predictions, policy integrations. By using machine learning outputs to shape global climate policies and promote adaptive infrastructure planning. And the last is to share platform for climate change data and machine learning research, which can accelerate progress in addressing climate change challenges under global collaborations. Conclusion and recommendations. The global scale impact. Machine learning offers unprecedented opportunity to enhance climate prediction and mitigation strategies. It gives us that opportunity to offer unprecedented opportunity to enhance climate change predictions. That is how important the machine learning models are. Then also key climate indicators. It provides a very good precision and maximum temperature indicates the crucial role for in forecasting future climate variabilities. So machine learning provides that opportunity and give us some kind of climate change indicators in terms of temperatures, in terms of future forecastings, and in terms of the weather change and the weather patterns. And the last one is policy making and understanding. The innovative of machine learning models and application enable us to understand and also prepare us and the policymaker for future, and also assist us to invest more in climate change tracking device or instrument for monitoring temperature and precision, which is essential for readiness for change weather pattern across in the global arena. Therefore, the summary of machine learning techniques and summary is that one is deep learning, which is CNN analyze satellite imagery for demonstration and alignment. The second one is time series model, RNN and LSTMs, forecast climate trend. Unsupervised learning, that's clustering, which reveal climate anomalies and regional weather patterns. The observation is that the actionable insights support climate adaptations to change weather is very, very critical. Thank you so much for the opportunity and for your time. Thank you.